let's take stock of the equations we have so far. We have three equilibrium equations in the x, y, and z directions. These are partial differential equations, and these are the governing equations. Then we have 6 equations from the stress-strain relations, 3D Hooke's law in our case, and we have 6 relations from the strain displacement relations. So we have a total of 6 plus 6 plus 3, 15 equations. Unknown functions, we have 6 stress components, 6 strain components, and 3 displacement components, u, v, and w. So we have 3 plus 6, 15 unknown functions. So we have enough equations for the unknown functions. And in the finite element method, we take the primary unknowns to be the displacements, u, v, w. And then we can express the equilibrium equations, which we have written in terms of the stress components, but we can express it in terms of the primary unknowns, u, v, and w. And you can do that by substituting the strain displacement relations into the stress-strain relation. So you'll get the stresses in terms of the displacements. And then you can substitute that into the equilibrium equations. And so in effect, you can get the equilibrium equations in terms of the 3 primary unknowns. And this means that if I look at, say, the equilibrium equation in the x direction, I would be replacing this with really derivatives of the displacements, du, dx, du, dy, etc. And similarly for all the stress components. And so you can think of this as a second order PDE effectively in u, v, and w, and similarly the other 2 equilibrium equations. So when I see this, I'll say, oh, and that in effect is a second order PDE in the primary unknowns u, v, and w. You don't do the substitution explicitly in the finite element method. You do this while deriving the algebraic equations, since the finite element method works by replacing differential equations with algebraic equations through some approximations, as you've seen probably elsewhere, or as we will see in a little bit. And to see these as second order PDEs, you can use a 1D analogy where the substitution is straightforward. So I like to think of a 1D analogy where now I have only one stress component, and that is a function of only x. So there is no dependence in y and z. And this is the only term that will remain, only derivative that will remain, and it will become, I can write this as an total derivative. So it becomes an ODE. And let me, just to keep things interesting, let me say the body force is not 0. Okay, so that's my equilibrium equation. That'll be my governing equation in 1D. And then I bring in, to write this in terms of the displacement, I will bring in the stress-strain relation, which will just be sigma xx is E epsilon xx. And then to write the strain in terms of the displacement, I'll bring in the strain displacement relation, which will be epsilon xx is du dx. So I can substitute this in here, and then that in here, and I will get e d squared u dx squared plus f of x is equal to 0. So you can see how I replace the equilibrium equation with in terms of the stress component. I replace it with the displacement, and so I have an equation for the displacements. And so that's the trick you play in the finite element method, but you don't do this explicitly. You do this when you derive the algebraic equations.